Hey everyone, we are ready to start. So 5 p.m., how is everybody doing? Still some energy left? Are you liking DevFest this year? Good, bad? Awesome. So we have the final presentation of the day. We have a keynote, but that's not the last thing we're going to be doing today. So very quickly, you should know that after the keynote, we are going to have prizes. So the raffle is going to happen here. After that, we're going to have the derby race, these crazy robots that you've seen in the atrium. We're going to go outside to the atrium, and we're going to see them race. And after that, we have happy hour. So everybody relax, network, have a drink, and have a good time. So make sure that you stick around after the keynote and that you basically enjoy the full experience. Awesome. So now let's go with the keynote. So it's my pleasure to introduce you to Sara Robinson. And this is actually my second time in a row in 2 days introducing her, because she was in DC yesterday doing a very similar presentation to the local DC community. So she's going to be doing a very similar presentation today. She was a developer advocate for Google for Cloud ML. Hopefully she's still that today. And she's going to be talking to us about how to build a machine learning model from scratch, and you're going to see it in very practical terms. Something I really enjoy about this presentation is that we've seen today many ways to apply AI and ML to a company. We've seen how to dig deeper into models, how to use them on mobile, how to play with TensorFlow to do specific things. Something I really like about this presentation is that it's going to be very practical. We're going to see actual code, and we're going to see it end-to-end. She's going to start with importing the libraries, and we're going to see how we load the data, how we process that data, how we create a model, how we host it on the cloud, and we can use it to actually have predictions. So super cool to be able to do machine learning in practice. All right, so thank you so much, everybody, for coming. And Sara, whenever you're ready.
I'm good. Thank you. Hello, everyone. Welcome to Live Coding a Machine Learning Model from Scratch. My name is Sara Robinson. I'm a developer advocate on the Google Cloud Platform team focused on machine learning. I won't describe what a developer advocate is because you've heard from lots of people on my team throughout the day. You can find me on Twitter at srobtweets, and I recently started blogging at sararobinson.dev. You should all grab your .dev domains while they're still out there. So I'm going to dive right in. What are we going to cover today? I'm going to start with a high-level overview of what machine learning is. Then I'm going to give an overview of the model that we'll be building. And finally, as promised in the title, we will get into some live coding. So to start, what is machine learning? I really like this definition, using data to answer questions. So this means that as we provide more and more data to our machine learning systems, they'll improve and they'll be able to generalize on new examples that they haven't seen before. So we can think of almost any supervised learning problem in this way. Supervised learning means we provide labeled training inputs to our model. Some magic happens in our model, and then it outputs a prediction. Now these training inputs could really be anything. It could be text, and maybe our model outputs the sentiment of that text, in this case, a movie review. It could be tabular data, numerical or categorical. So in this example, maybe we've got some fitness data on our activity for the day, and our model predicts the quality of the sleep we'll get that night. We could also have images. So our model could take pixels in this image as input and output the label cat. So it seems like a lot of magic is happening in this machine learning model circle, but it's actually not magic. All it boils down to under the hood is a bunch of matrix multiplication. So if anybody remembers y equals mx plus b from their algebra classes, this may look familiar. So basically what you do is you take your features and you turn them into matrices. That's the inputs matrix. And then you have these weight and bias matrices, and these are initialized with random values. So the idea is that when you start training a machine learning model, these are randomized. And as you continue training, you want to find the optimal values for these weight and bias matrices to get high accuracy predictions. So that sounds great at a high level. But none of the examples that I showed on the previous slides were in a matrix format. So how do we represent data as matrices? And it turns out pretty much any data type you can think of can be turned into a matrix. So if we take an image as an example, all an image really is a bunch of pixel values. In this case, we have a color image, so every pixel in the image has a red, green, and blue, or RGB value. So all this image turns into is 3 matrices with the RGB values for each pixel. Let's say we have categorical data. So maybe one column in our data set is the industry that a particular person works in. And to keep it simple, let's say there's only 3, healthcare, finance, and retail. So the way we represent this is through what's called one-hot encoding, where you take an array, and the number of elements will be equal to the number of possible values. All of the values will be 0, except for 1, and the index of that 1 corresponds with the actual value for that category. Now you might be thinking, wouldn't it be a little bit simpler if we just numerically encoded these, so healthcare was 1, finance 2, et cetera? You could do that, it might be a little bit easier, but the problem there is then our model will interpret these as continuous numerical values. So it'll assign a higher weight to retail if we convert that to a 3. So we can solve that problem by one-hot encoding our categorical data. So I'm also going to talk about text data later on. That'll be the focus of our model. But I want to show you in this talk all of the machine learning tools that we have on Google Cloud. And I'll hone in on just a few of these when we live code our model. So I like to represent all of our ML offerings in a pyramid. And the pyramid is organized by levels of abstraction, where the products that are towards the bottom are targeted more towards data scientists, machine learning engineers. As we move towards the top, we have lots of tools that don't require any machine learning experience at all to get started. You just bring your own data, you can press a button to train a custom machine learning model. So I'm not going to get into all of these right now, but we are going to focus on 2 of them, so I'll talk about that briefly. So at the bottom of the pyramid is not a product per se, but we have these open source machine learning frameworks. So if you're building an ML model from scratch, not using any tools to help any products, you would start with one of these frameworks. TensorFlow is a popular machine learning framework created by Google. XGBoost, scikit-learn, PyTorch are all other great open source frameworks. And then we're going to use Cloud AI Platform prediction to serve our model. So what AI Platform training and prediction lets you do is bring your custom model code, and you can use Google Cloud infrastructure to train your model, and then you can also deploy your model to Google Cloud to serve it to scalably generate predictions from your trained model. So we're going to be focusing on those 2 for now. If you're interested in AutoML, BQML, those let you bring your own data, train a model by just pressing a train button. You don't need to write any of that underlying model code. If you're interested in that, I've got some other talks on that. I can share resources with you after. So let's dive into what we're going to build. And when I was thinking about what demo I wanted to use for this, I wanted to choose something that would resonate with developers. And as I was thinking about it, I realized that there was one tool that I use on a daily basis, maybe even multiple times a day. Can anybody guess what it is? You can shout it out. Slack? No, not Slack, but close. I do use chat apps every day. The answer is Stack Overflow. So I'm sure most of you can relate. So the model that we're going to be building is a text classification model using data from Stack Overflow. So our model inputs will be Stack Overflow questions. And because we're building a custom model, we're starting from scratch, we need a lot of training data to get started. And luckily, we have a public data set that we can use for this. So BigQuery is our big data analytics warehouse on Google Cloud. And as part of BigQuery, they have this thing called the Public Datasets program, where they provide tons of open data sets that anybody can download, query, play around with. One of those happens to be a data set of tons and tons of Stack Overflow questions. At the time, and it's continually updated. So at the time I took this screenshot, there was over 26 gigabytes of questions and over 17 million questions in there. So tons and tons of data will be plenty for training our model. So we're not going to use all 17 million questions to train the model, because that would take way more time than we have together today. So I limited the problem space a bit to just include 5 tags related to machine learning and data science. So our model will take as input the title and the body of the question, and then it'll predict the tag or tags. So for this example, it would predict pandas. Our model will also be able to predict more than one tag for a question, because as you know, many Stack Overflow questions have lots of tags. So the first step in building this model is getting the data from BigQuery. For those of you that haven't used BigQuery, it has a great web UI where you can write your SQL queries directly in the browser, take a look at the results, download it as a CSV or JSON. So this is what our query looks like. We're getting all the questions that contain these 5 tags, concatenating the title and body, and then just replacing the bar with a comma so that we have a comma-separated list of all the tags. So I ran this query. I started looking at the results, and I noticed something, which led me to think, do we even need machine learning for this? What I noticed is that a lot of the question posters were very helpful, and they put the name of the framework they were using in their question. So I was thinking, can we replace our entire machine learning system with a giant if statement? If TensorFlow is in the question, the tag is TensorFlow. And well, that would work for some questions. We also have questions where the poster will just dive right into asking the question without putting any indication of the framework name per se. And it's still a really good question, but it doesn't include the name of the framework. And we want to include questions like this too. So I wanted a way to prevent my model from picking up only on those framework names as signal words. So I wanted to get rid of all those and replace them with something. And I love avocados. So I decided to replace all of these things with avocado. And I didn't just take the tag names, also took popular abbreviations. So you often import TensorFlow as TF. So we removed TF, PLT for matplotlib, et cetera. So the result is a data set with a lot of avocados. We get avocado predictive model questions, finding code on avocado website, lots of avocados everywhere, which is pretty fun. So we've got our data. The next step is preparing our data. So we can't feed that text directly into our model. We need a way to encode it numerically. And there's many different approaches for encoding text data. I'm going to use one called bag of words. I think this is the simplest one to get started with. So when you're thinking about bag of words, you can think of each example input to your model as a bag of Scrabble tiles, where instead of a letter on each tile, you have a word on each tile. So the bag of words approach does not take into account the order of words in a sentence, because it's a bag, it's all jumbled up. It does take into account the presence or absence of certain words. If you're interested in word order and text generation, there's other encoding types and models that you can use. So we'll see how this works with a really simple example. For this example, let's pretend that there's only 10 words in our vocabulary. So maybe we're learning English for the first time, and these are the only 10 words we know. This is how our model will approach the problem. And this vocabulary, these are going to be the top 10 words from our entire data set of questions. And for this, we'll say we only have questions about pandas, keras, and matplotlib. So these are the only words we know. So what happens when we get a question like this? How to plot data frame bar graph. These 3 words from our vocabulary light up because those are in the question. So the way we represent this in a matrix is we have this vocabulary array where each index in the vocabulary corresponds with the word from the vocabulary. So the first index becomes a 1 because data frame is in this question, and then we have 1s for graph and plot as well. And notice that even though plot comes before data frame, it's after data frame because the array is based on the order of that vocabulary. So just to summarize how it works, we have our inputs. They get turned into this vocabulary size array. And then they get turned into this multi-hot vector of 1s and 0s. For the prediction, it's pretty simple. It's also, in this case, going to be a multi-hot array because there's multiple possible labels per question. And what will our model look like? So our model is going to take as input that bag of words matrix, however big we decide to make our vocabulary. Now, choosing your vocabulary size depends a lot on the number of total unique words in your entire text data set. If you picked something too small, the vocabulary will only include really common words like the, is, and you won't really capture any meaning from your input data. If your vocabulary size is too big, you'll end up with matrices of almost all 1s, which also won't be super meaningful. So it's worth playing around and trying different values till you find the right one. So we'll take as input an array the size of our bag of words matrix for each question. Then we're going to have 2 what's called hidden layers. So the reason this is a deep model is because we have layers that are in between our input and our output layer. Now, we don't necessarily care too much about the output of these hidden layers, but our model obviously does. Our model is using these layers to represent more complex relationships in our data. The output layer, to compute the output layer, we use a function called sigmoid. And what this does is it creates an output layer of the total number of possible labels in our data set. In this case, we have 5 possible tags. And each value is a float from 0 to 1, indicating the probability that that tag is associated with a particular input question. You may be familiar with a function called softmax. Softmax is very similar to sigmoid, but it's for models that only have 1 label per input. And so for softmax, all of the values of this would add up to 0. But since we're using sigmoid, it could have multiple tags per question. So that's why we do that here. And so let's look at all of the tools we're going to be using to build our model. To pre-process data, we already saw that we'll be using BigQuery for that. We're going to be using Pandas, scikit-learn, and Keras to do some pre-processing on our data, get it ready for our model. We'll be building our model with TensorFlow. And we're going to write the code, train, and evaluate our model in Colab. Colab is an interactive Python notebook that's based in the browser, completely free. I'm curious, how many of you have used Colab before? OK, looks like about a third. And so once we train our model will train super fast. So we don't need to train it on the cloud. But we will then deploy it to the cloud so that we can make predictions on our trained model from anywhere. So as promised in the title, there will be live coding. So let's get to the code. So here we have our Colab notebook. How is the font size? Thumbs up? Good? OK. All right, I'll leave it here. So as you can see, we have a totally empty Colab notebook with just some comments. What could go wrong? Live demos. You never know. We'll find out. So we're going to dive right in. The first step is to import all the libraries we'll be using. Colab has a really handy feature that lets you write custom snippets. So I'm not going to live code the entire thing. I've written some custom snippets that I'm going to paste in. So the first one we'll grab is the one to import our libraries. There we go. So if we run this, we are importing our libraries, making sure we're using the right TensorFlow version. This demo failed last night, by the way, because of versioning issues. So trying to prevent against that. The next thing we'll do is authenticate to our cloud account. Colab has a handy authentication method. And what we'll do is it will give us a link. And we'll just copy paste this code once we authenticate. We're going to do this because I have some resources in my cloud storage bucket that we're going to use to download the data. So we just need to paste this code in here. And then we should be authenticated. Looks like we're good. So the next step is to download our data. Now we're getting into the fun part. So first, we will download the CSV. So I'm skipping the part where I extract the data from BigQuery. I already did that. I saved it to a CSV file. So we're going to download it to this Colab instance. It's got 188 total questions. So the next step is actually going to make it one size bigger. There we go. We're going to read the data into what's called a Pandas data frame. Pandas is a really handy library for all sorts of data science things. And the data frame is just one of their objects for reading in data. So we'll call pd.readCSV. And we'll pass it that file up there. An important concept in machine learning is shuffling your data. It's really important if, say, your data is in alphabetical or numerical order. You want to make sure it's shuffled so that when you split it into your train and test sets, it's pretty equally distributed. So in order to shuffle it, we just need to pick a random state. I like the number 22, so we're going to go with that. And then this function will give us a preview of our data. So this is what our data looks like. We've got our text, and then we've got our tags as comma-delimited strings. As we know, it's not ready to feed into our model yet. We need to convert both the tags, our labels, and our text to array format. So first, let's take care of the tags. So I've written some code here to encode our tags. And by the way, I'll share a link to all this code at the end. So we'll run this. And what this is doing is it's first splitting our tag strings by comma and creating arrays. And then I'm using this scikit-learn utility called multi-label binarizer, which is turning those arrays into this 5-element label vector of ones and zeros. So for the first question, it's about Keras and TensorFlow. Next step is to split our data. So the reason we split our data in machine learning is usually we'll take the majority of our data. Often people use 80-20. So we'll take 80% of our data and use that to train our model. We want to reserve the rest of our data to test our model on data that it's never seen before, so that we're not cheating. So we've got our train size. Again, our data set has about 188,000 questions total. Our next step is to split our labels into our train array and our test array. So we'll call it train tags is equal to tags encoded up to train size. That's just this array from up here. And then test tags will be equal to tags encoded of the rest of them. So we'll run that. And the next thing we want to do is tokenize that. So luckily, we don't have to go through that whole process of getting the top n words from our word corpus and converting that into multi-hot arrays. We don't have to do that by hand. Keras has a really nice utility function for us to do that called the Tokenizer. So I've written a class to do that for us, and I'll explain what's going on here. So in this text preprocessor class, this method is creating the tokenizer. To do that, we just pass it the size of the vocabulary we've chosen. And this transform text is using Keras's text to matrix function, which will take our raw text and convert it into a vector of ones and zeros. So let's actually make use of that class. So first we'll import it. And the next thing we want to do is we want to split our questions into the train and test arrays before we transform them. So we'll call this train questions, and it's equal to data of text.values up to train size, and then test questions is the rest of them. Move that up to the top. So the number that I found worked best for our vocabulary size for this example is 400. So we'll save that to a global variable. It depends a lot on your specific data set. And then we'll actually create an instance of this text preprocessor class. So we'll say this is equal to text preprocessor, and we'll pass it our vocabulary size. Now to actually create that tokenizer, we'll call this create tokenizer method. And we need to pass this our train questions. So those are just the raw strings of the Stack Overflow questions. So we're almost ready to create those multi-hot bag of words arrays. All we do is we use this class method transform text and pass it our train questions. And then we'll do the same for our test set. And we'll pass it our test questions. So this is going to take a while to run, because what it's doing is it's taking our 180,000 examples, converting them from raw text to multi-hot bag of words arrays. Luckily, while it's running, we can keep writing code. So after that's done, I'm just going to print the length of the first element of that bag of words array. It should be 400. And then we'll actually print the first one just so you can see what it looks like. We'll go back up here once it finishes. So the next step is actually writing the code for the layers of our model. And the first thing we want to do is save this tokenizer that we created. The reason that we need to save it is so that we can use it when we make predictions and also when we deploy our model to the cloud. So I'm going to use a Python utility called pickle, which will just save this object to a pickle file so that we can use it later. And the next step is actually writing the code for our model. So we'll do that. I'm going to wrap it in a create model method, which will take in our vocabulary size and our number of tags. And to create our model, I'm using the Keras API, which is part of TensorFlow. I imported it up above. And specifically, we're going to use the Keras sequential model API, which essentially lets us build our model as a stack of layers. So quickly, we'll go back here. We see that our bag of words matrices were created. And this is what the first one looks like. Looks like a good mix of ones and zeros. So now that that's ready, back to writing our model code. So I'll explain what this is doing in a moment. So the first layer of our model takes as input an array the size of our vocabulary, in this case 400. And then it's going to transform that 400 element layer into a 50 neuron layer. This is just a number that I found works best for this particular model. The word dense here just means that it's a fully connected layer. So this means that every neuron in the input layer, which is size of 400, is connected to every neuron in the output layer, which is going to be 50. The last thing I need to tell it to create my first layer is the activation function I'm going to use. This is how our model computes the output of the layer. The great thing about this with Keras is we don't really have to know how this particular function is implemented under the hood. Don't really have time to go over it in this talk, but you can definitely read up on it if you're interested. So in this case, we're going to use ReLU. This is for our hidden layer. We have one more hidden layer that's going to be of size 25. And we don't need to tell it the shape, because it'll infer that. So we just need to tell it the activation function. And then finally, we have our output layer, which is of size num tags. And remember that the activation function here is going to be sigmoid. So we've essentially written our entire model in just 4 lines of code, which is pretty cool. And the next thing we need to do so that we can run this is call model.compile. And we pass this a couple of things. So we need to tell it the loss function we're going to use. Loss is how our model calculates error. So it's the thing that our model is trying to minimize throughout training. And this is a loss function that works well for this particular multi-label problem. We also need to tell it the optimizer function we're using. This is how our model, the algorithm our model will use to update the weights after each training iteration. So Atom is the particular algorithm we're using there. And then finally, we need to tell it the metrics we want it to give us as it goes through training. In this case, we'll just get accuracy as a percentage. So then we'll return the model. And next thing is we actually want to create an instance of this model. So we'll call create model. We'll pass it our vocab size, which is 400, and the number of tags, which is 5. And then Keras has this handy model.summary method, which will print out a summary of our model, the number of trainable parameters in it. So we've created our model. We've got our data ready for it. Now we're ready to train it. So to do that, we call model.fit, and we'll pass it our bag of words training array. Let me push this to the top. We'll pass it our training labels. And then we also need to tell Keras how many epochs we want to run training for. So what this means is this is how many times our model will go through the entire data set, all those 150 questions. We also need to tell it the batch size, which is how many elements our model will look at once before it updates the weights, before it runs that optimizer function. And then I'm going to add one optional parameter here called validation split. And I'll run that while I talk about it. What validation split does is it takes a subset, in this case 10% of the training data, holds it, and after each training iteration, it runs a test to see how the model's performing. So our training finished, and what we see here is our accuracy is going up, and our loss is going down, which is a good sign. What we also notice is that in addition to our training loss decreasing, our validation loss is also decreasing, which is good. So one reason that validation split can be super helpful is if your model takes a long time to train, you want to make sure that as your training loss decreases, your validation loss is also decreasing. If it's increasing, it might be a sign that your model is overfitting. So the next step is to evaluate our model on our test set. So here we'll pass it our test questions, our test tags, and also our batch size. And it looks like our accuracy is similar, 96.02 compared to 96.1%. So we've created our model. The next thing we want to do is save our model. So we'll save it to a file. And Keras uses the H5 file format for saving models. So we saved our model to a file. It's just saved on this Colab instance. And right now we're going to test it locally. So I've written a class for us to do that. What this is, it's taking care of the pre-processing on our data, so it's converting the text to bag of words. It's loading up our model and our tokenizer and returning a prediction. So the next step is to save some questions for prediction. And finally, make a prediction on our model. So it's just using this array of 2 questions as an example. So for the first question, it predicted Keras, which looks about right. Second question, it predicted pandas. So our model is working well locally. our next step is to deploy it to the cloud. So to deploy it to AI platform, we'll first package it up. So we'll run that. Next step is we need to copy a couple of files to Google Cloud Storage so that Cloud AI Platform can read it. So we'll copy our save model file that we just saved along with our tokenizer that we saved to that pickle file. Then we will set gcloud. Gcloud is the Google Cloud CLI. And we will set it to the projects that I'm going to use for this demo. You can run bash commands right in Colab too. Just put a bash in the front. And then finally, we are going to deploy our model. So to deploy it, we're going to make use of this new feature on Cloud AI Platform called custom code. I'm going to deploy it first, then I'll explain. So we're going to create a new version. We'll call it DevFestDc. And what custom code lets us do is it lets us write custom server-side Python code that's run at prediction time. So the reason this is really useful for text models specifically is we can keep the client super simple. The client can just send the raw text right to our model. On the server, it'll take care of converting that text to our bag of words matrices and returning a prediction. So that's why we created that custom model class up here. So we're sending that to the cloud when we deploy our model. So if we go over here to our model UI, we can see that our new model is deploying, which is pretty cool. That will take a bit of time, so I'm going to go back to the slides. Oops. And so we just trained our model. It's looking pretty good. It's got 96% accuracy. But I'm wondering if we can do better. So what I mean by that is right now our model is a black box. We know that it's making certain predictions of tags for a particular question, but we don't really know why it's making those predictions or how it's coming to that conclusion. So can we uncover the black box? The reason this is really important is that as model builders, we are responsible for the predictions that our models generate. And we want to make sure that our models are not making biased decisions. And one way we can do that is making sure that the training data is representative of anybody who's going to be using our model. Another way this would be helpful is if we could see how our model is making that prediction to determine if it is biased. And luckily, there's a bunch of great open source tools that can help us with this. The one that I'm going to use in a moment is called SHAP. It's open source on GitHub. You can check it out. What SHAP lets us do is it lets us explain the output of pretty much any machine learning model. Works for multiple data types, works with TensorFlow, scikit-learn, XGBoost, PyTorch. So we're going to use SHAP. The way we use SHAP is we create what's called an explainer object. In this case, we use deep explainer. And we pass it a subset of our training data. And then what SHAP will give us back is what's called these SHAP values. And what these are attribution values for each of our features. So high positive SHAP values mean that this particular feature was more important in our model's prediction. Negative values indicate that this particular feature pushed our model's predictions down. So the way this is represented for our bag of words data is, remember, we have that 400 element vocabulary array. That's our input to our model. So if we feed this into SHAP, it'll essentially treat that as 400 different features. So we can grab the top however many values we want from that array to see which words were most impactful in our model's prediction. So I wrote some code to visualize this. You'll see it in the notebook in a moment if we have time. So for this particular example, the correct tag was pandas. And the words that are in blue are the words that contributed most to our model's prediction. So the words here were column, data frame, DF, series. And this is a good sign, because these are words that are pretty common to pandas. If you use pandas before, you might recognize this. And then the words that our model picked up on least were for, each, and you, words that might be common across any Stack Overflow tag. So if instead we saw that our model was using these very common words to make predictions, that might be a red flag that we need to go fix our training data. One way this would be useful in avoiding bias is if you take a text sentiment model as an example, you want to make sure that your model is not using certain identity words to influence its sentiment if it shouldn't be. So let's go back to the code. So it looks like our DevFest model has deployed, which is exciting. So now we're going to generate some predictions on our deployed model. So first we will write a file with some test predictions. And then we're going to use the gcloud CLI to get our predictions. So we'll say predictions is equal to gcloud AI platform predict. We need to pass it our model, which is called Stacko model. And then we pass it our text instances, which is this text file that we just wrote, predictions.txt. And so that we know that I'm not cheating, I'm going to change this to the default. So now DevFestDc is my default model. So it'll use that to get the predictions. And then it would be useful if we printed them out. And this should be our sigmoid arrays. So it's getting predictions on that model that we just deployed, which is pretty cool. To actually make sense of this, I wrote a little helper function to just visualize the tags that it's predicting, which should be the same as what we saw above, because it's the same model. And yeah, so the first one is predicting Keras, which I think is this first index, and then this one is predicting pandas, which is probably this one, 80% confidence. So in the remaining time, I'll show you how we can use SHAP to explain the output of our model. So the first thing that we'll do is install SHAP. And we'll also install this module called Colored, which I use to color the text in the screenshot I showed. So Colab comes with tons of awesome frameworks pre-installed. It doesn't currently have SHAP and Colored, so you can just install extra modules with an easy pip install right in Colab. So we've installed them. We'll import SHAP, and then we will create our explainer. So our explainer will be a deep explainer, and we'll pass it the first 200 examples from our training data set. And then we want to create our SHAP values, which will be equal to explainer.SHAP values. And we'll get the SHAP values for, let's do the first 25 examples from our test set. So, oops, let's see what I did here. SHAP.deep, oh, I'm missing my model parameter. You have to pass your model when you create the explainer. Let's try that again. There we go. Okay, so now we have our SHAP values, and the next thing we want to do is, I've just written this utility function, so that tokenizer we created above is actually a dictionary, so that we can see which attribution values are associated with which word. We're just going to convert it to a list. And this will actually let us see what words are in our vocabulary, so the top words that our 400 element vocabulary is using. The first one is an empty string because for some reason the tokenizer is indexed by 1, and this is 0 index, so I added the empty string. But the rest of these are words that are in our vocabulary. So you can see that the first few are super common, but as we scroll, we see some words that are more common to specific frameworks. So what I want to do next is print the summary plot. And so what this will do is it'll tell us for these 25 test examples, what are the most popular words that our model is picking up on. So we pass it our SHAP values. We'll also pass it the feature names, which is this array we just created, along with our class names, which we can get by doing that. So we should see a nice graph here. So what this graph is telling us is which words our model used most to make predictions. So we can see data frame was the most used signal word, and this breaks it down by class. So it was the most used signal word for pandas, and this is magnitude, so absolute value of each SHAP attribution value. So it was also a signal word for these other frameworks. Chances are it was probably a negative signal word for these. So it's signal, data frame signal, this question is probably about pandas, but it's probably not about these other frameworks. Plot, we can see was most used by Matplotlib, DF, pandas also. So we can see all of those as we go through here. But it would be nice for each individual question, maybe this is something you'd want to surface to your end users, to see which words contributed to the prediction. We'd want to highlight words for individual questions. So I've written a couple functions to do that, and we'll just paste that in. And we'll print it out for a couple of questions. So this question about pandas, we get column, not a number. We get a lot of NaN values in pandas data frames. And DF1 and DF2 are common names that people call their data frames, so that's looking good. For TensorFlow, the words that it's picking up on are sesh, tensor, ops, Keras, LSTM is a type of layer. Dense is also a type of layer, as we saw. I'm just grabbing the top 5 highest attribution words. So there could be others that are still used, but less so in here. TensorFlow, again, we get graph, float32, placeholder. These are common words in TensorFlow. And then finally, matplotlib, we get figure, plot, grid. So it looks like our model is picking up on the right signals to make predictions. So that is the demo. I'm going to go back to the slides. And I know I covered a ton of things, so just a quick summary of what we built. We built a custom text classification model using tf.keras. We deployed it to Cloud AI Platform and got predictions back. And then we explained our model output with SHAP. So thank you. And also thank you to Capital One and all of the awesome DevFestDc organizers for putting on this great event. I've got links to a bunch of the resources. So all the code from that notebook is at this bit.ly link. If you're interested in AI platform, go here. And one more thing I want to mention is that we are working on model interpretability support on Cloud AI Platform. If you've got a use case for that or interested, we would love to hear from you. We have this form to just express interest in it, and we will follow up with you. So please follow this bit.ly link if you're interested in doing that sort of thing that I did with SHAP on Cloud AI Platform. Thanks, everyone.